let's continue with part B, 11.3. This time we're going to estimate the remainder and sum of a series that satisfy the three hypotheses of this integral test. Okay. So what are the three hypotheses of the integral test? Function has to be what? Continuous, positive, and decreasing. Okay. So if a series that the relating function satisfies these three, we can actually estimate the remainder and the sum. Okay. So first, let's talk about the remainder. Okay, what's the remainder? The n partial sum is the sum of the first n term. Okay, so this is from a1 all the way up to an. And if you just stop here and discard this, then this is Sn. Okay, and then the rest over here is called Rn. That's called the remainder Rn. Rn here basically is the part that the sum take away this Fn. Okay, take away this part here. Then this is Rn. Notice that, do you notice the index over here? The first thing in the remainder Rn is actually n plus 1. Okay, so pay attention. The first chain over here in this remainder, the index is n plus 1 because you chop it off over here. Okay, this is Sn, this is Rn. Okay. So if the relating function satisfies these three, okay, we try to estimate the remainder Rn. So we want to see how big this remainder here could be. Again, we're going to do the similar trick as before. Remember the function is decreasing. Okay, so it goes down like this. Now we're going to start from n. Okay, so this is looking at this start from n over here because we're looking at the remainder. Okay, so start from n. Now, because the function is decreasing, if I use the right endpoint as a height for those rectangles, so all those rectangles is going to be under the curve, okay, because it's decreasing function. Right endpoint is the lowest point. So it's going to be under the curve. Okay. Now, this one here is, well, the index over here is n plus 1. The height of this is a of n plus 1. Okay. The function value is a of n plus 1. This index here is n plus 2. The height of that is a of n plus 2 because this function is related to the series. Remember, replace the n by x, right? So this is a of n plus 1. This is a of n plus 2. And this one here, think about that because the width for each rectangle is 1. So 1 times 1 height. The area of this rectangle is also a of n plus 1. And then 1 over here times a of n plus 1 is the area here. So put together, if you sum up all those rectangles, then does it look like this is Rn? Is it Rn? Yeah, remember the definition for Rn, right? So Rn over here is from an plus 1 plus an plus 2, etc. Continue on, right? If I want more terms over here of a of n plus 2 and then plus etc. Okay. The first term over here, it is going to be a of n plus 1. Okay. So this is a of n plus 1 and then plus a of n plus 2, etc. So this is Rn. Okay, is the sum take away Sn. Okay, so you have this. It's the sum of those rectangles over here. Comparing that to the area under the curve from n on. So here is n. The area under the curve from n on. Well, we have this extra space over here. So the sum of this is going to be less than or equal to the area under the curve. When it's under the curve right here. Okay? So the area under the curve is this integral from n integral of the function n go from x go from n to infinity. So we know Rn is less than or equal to the integral of this function x go from n to infinity. Do you guys agree? Yes. Okay. All right. Now, I'm going to take away some because I'm trying to let you guys discover this. Okay. Okay. All right. Okay, let's try this way. Okay. What about this time? I'm going to use the left hand form. Okay, I'm going to use the left hand form. So this index here is m plus 1, and here is m plus 2. Okay. Okay, so this is m plus 1, and this is m plus 2. Okay, then the height of this is going to be, what is this? Then this is a of m plus 1, right? Okay, and this is a of m plus 2. Okay, and then etc. Right? What's the area of this rectangle? When I use this left hand form here, what's the area of this rectangle? This first one, this one right here. 1 times the height. What's the height over here? Am plus 1. So it's am plus 1. Agree? Right? So let me put the relation over here. So this going to this, right? The area of that. And then this one here, am plus 2 is the area of the second rectangle. And then continue, right? Okay, etc. Okay. Now, if you sum this up, is this Rn? Yeah, Rn start from am plus 1 on, right? Okay, like this. Okay. Now, comparing this, now because this is a decreasing function, when we use the left hand form, would those rectangles be above the curve? Yeah, above the curve. Okay. And this time it's going to go from, so above the curve. So comparing the sum of those rectangles to the area under the curve from this n plus 1 on, from here on. Okay, so this time we're going to compare to from here on. Okay, from here on. M plus 1 on. Okay, m plus 1 on. Okay, from here on. The sum of those rectangles bigger or the area under the curve bigger from here on? The sum of rectangle bigger, right? Okay, good. You got it. Okay, so this. So so the sum of the rectangle is bigger. And what's the area under the curve from this index on? If you want to express that using an integral, what would that be? Integral of the function, and the function is f of x. Okay, ex. X go from what to what? M plus 1. Yes, good job. Okay, so it is m plus 1 and m to what? Infinity. Yes, you got it. Good job. Okay. Okay. Now, we actually found that what happened to the Rn. Okay, we put them together. Rn is actually less than or equal to this integral, but greater than or equal to this integral, right? Okay, so we see that Rn is less than or equal to this integral here. This is the lower limit here is n, but then greater than or equal to this integral, the lower limit here is n plus 1. Okay. So m plus 1, n plus 1. Okay, you see it? Okay. So this provides us an estimate for the remainder. So the remainder is no less than this and no more than this. Okay, so that gives you we made the estimate for the integral test. So that's the one that you probably need to use it for your homework. Okay, so remember this. So try to remember this. Okay. All right. So how do you remember this? A trick to remember here is the index here. Rn is going to be bounded above by integral that start with n, and then bounded below by this integral start with n plus 1. Okay. This one start from n is actually is bigger, right? Think about that, the area under the curve from n on. This integral here is actually smaller than this integral. The start from n plus 1 on is this green one, right? Okay. All right. So the remainder Rn is bounded by this two integral. This start from n, this start from n plus 1. Okay. If the function is continued positive and decreasing from n on. Okay. How about we try some example? Okay, let's try this example using the remainder estimate for the integral test. Approximate the sum of the series by using the sum of the first 10 terms. Okay, so what is the series right there? Okay, let's write down. So this is a series 1 over n cubed. First of all, I'm going to ask you, this series here converge or diverge? Why? Yeah, P here is greater than 1. It's a P series, right? So P is equal to 3, which is greater than 1. So this P series over here converge, right? So we know that it's equal to a finite number, okay? So we know that. Now we're going to approximate the sum, okay? But we don't have infinite many amount of time, right? So we can't add all of them, continue forever. So we could approximate that. So this series over here is, well, what is it? Let's write down the first couple of terms. So it is the first term, okay, index here ends up from 1 to infinity. So the first term will be what? 1 over 1 cube, 1 over 2 cube, 1 over 3 cube, and then all the way. And the first 10 term, the last, what about the 10 term? 1 over 10 cube, right? So we're going to just use this to approximate the sum because you're supposed to have more at the end, right? But how about we just stop here and say, how about I just use this to approximate the sum? Do you guys have a calculator? Could you guys plug it in? I know this graphing calculator can do the sum. If you don't punch in one by one, is there a way you can program or to do it? I know some of you already wrote the program for the Fibonacci sequence, right? Okay, it was a good one. So you can actually write programs to do something like this, a simple program. I actually gave you the result. Do you see the next page? It's right here. Yeah, I agree, right? So I did that. I added the first tension. I got this. Okay. So what are we trying to do? We try to estimate the error involved. So we say, how about I just stop here? I just add up the first 10 terms. Would that be good enough? Would that be good enough to approximate to the exact sum, right? Because we have infinite many terms. Okay. So we want to see how big is the error. Would the error be small enough to be acceptable? Okay. So we're trying to estimate this error, which is R10. Okay. Notice that R10 here, this index here start from 11. Okay. So how do we do this? According to the remainder estimate for integral tests, okay. Well, we need to actually check the condition of the hypothesis. Is the function here continuous? So what's the relating function? What is the function f? 1 over x cubed, right? Yeah, good. Is it continuous? Yes. Positive? on 1 to infinity, right? Okay, and is it decreasing? Yeah. The bigger the denominator, the smaller the quotient, right? Yeah. So it satisfies the 3 hypotheses. So you can use the remainder estimate, okay, for integral test. And what does the remainder estimate for integral test say? R of 10 is bounded below by what? Bounded above by what? Bounded below by n. Okay, let's see. Let's see. R of let's see. Oh, okay. The other way. Okay, so R of 10 bounded above by an integral, bounded below by integral, right? Okay. What is the above integral? Okay, maybe it's better that I write it down. Okay. So it's going to be bounded by integral here and integral here. Okay, of the function, which is the function here is 1 over x cubed, 1 over x cubed dx. Okay. What is the lower limit for this? 10. Yeah, the same index of this, right? So this is 10, then this is 10 to infinity. Yeah, you got it. Okay, good. Okay. Infinity. Okay, to infinity. Okay. And then this one here will be, yeah, you see it, right? It's 11, right? Okay. So it's 11. Okay. So you see the pattern, okay? The above integral here is the same, has the lower limit same as the index, and then this one here will be one more than that. Okay. Now we need to find this integral. What is this integral? Well, how about we just do it once? How about we find antideuty of 1 over x squared, 1 over x cubed? What's antideuty 1 over x cubed? Which is negative 1 over 2x squared is negative 1 over 2x squared, okay? So this one here is x to the negative power. So increase this by 1, so x to the negative second, and then divide by negative 2. So we got this, right? And now look at these two integrals. They're kind of similar, except the lower limit here are different, right? So how about we just say from n to, let's just say from n to infinity, and then we can substitute later, right? So n to infinity. So if we go from n to infinity, we're going to take the limit of this, okay? And let t go to infinity. This one go from n to t, right? Okay. N to t. And what does it equal to? What do you think? So limit as t go to infinity, substitute t in it, so it is negative 1 over 2t squared. And then minus become a plus 1 over 2n squared. As t go to infinity, what happened to this? What does it go to? It go to 0, right? Yeah, good job. Okay, so that part go to, this part over here go to 0, okay? And then this one here has no t in it, right? So when t go to infinity, it stays as itself. So it's not going to change. So this is 1 over 2 and square, right? Do you agree? Okay. So when the integral here go from n to infinity, it's 1 over 2n squared. Now we can put this, put that in here. So this integral is equal to what? According to this. 1 over, yes, right, you got it. So it's going to be 1 over 2 times 11 squared. Right? Okay, good. So, and then what about this one? It's 1 over, wonder is it the same person all the time? 1 over 2 times 10 squared, right? Okay, good. So it's going to be, oh, that's an equal, greater than equal to this, less than equal to this, okay? All right, so R of 10 is between this and this. And I did the calculation for this. This is 1.004132, okay? And can you do a calculation on this? That will be easy. 5, yeah. So between this and this, okay? So the size of the error, okay, so we know that R10 is going to be, using only the first 10 terms, is going to be at most this and at last this, okay? At most this and at last this. So the error is going to be no more than this, but more than, no less than this. Do you agree? It's kind of scary every time. Do you agree? Okay, I have to agree. What else can I do? Okay. Okay. Now the second part here is kind of small. Okay, so kind of small. So accuracy to within 0.0005. What is it? What does the problem say? How many chains are required to ensure that the sum is accurate to within 0.0005? So which means that now if I use only the first 10 chains, I know the errors is no more than 0.005, right? But now we want it to be better. I want it to be no more than 0.0005. This is one more zero, okay? So one more zero than this. So we have to get more chains. Instead of 10 chains, we need to get more chains. How many chains do you think we need? If we only have 10 chains, then the error is only no more than 0.005. But we want to get one more zero here. Remember, this one here has one more zero. Okay, 100 chains? Okay, let's find out. Let's find out. Okay, let's find out. So, do you remember the Rn? So basically, we just try to get this part of this inequality right here, right? This one right here. Okay. So we want Rn is less than what? Less than, what was it? Less than the integral. Yes, yes, very good. The integral, let me write down. Okay. The integral of n to infinity of this, right? Oh, I'm going to make it actually bigger. Let's see. Okay. 1 over nq dx. Okay. And from n to infinity, right? So we want it. Okay. And we already did this integral that is 1 over 2n squared. Okay. So remember, this is n, this is n, then this is 2n squared. Okay. So we know that Rn is less than or equal to this. Okay, this is a less than equal sign. So what do we want? We want this to be, if I can say this one here is less than or equal, or actually less than. When they say within means strictly less than. So there's no equal. So strictly less than 0.0005. If I can ensure that this is less than, if I can ensure this is less than this, does it ensure that Rn is less than this? Yeah, because this is less than or equal to this. And then if this is less than this, by translation, right? Then this is less than this, right? Okay, good. So you got it great. Now all we have to do here is to solve this inequality. Can you guys solve for n and tell me what is n equals to, n greater than? N squared is n squared, so multiply both sides by 2n squared. N squared is going to be greater than 1000. Yeah, so it's going to be greater than 1000. Good. So remember n has to be positive, right? So n is greater than what? Square root of 1000. What's square root of 1000? It's about 31.6. Okay, 31.6. So what does it mean? That means you need to have at least 31.6 turns, but you cannot have a 31.6 turns. So you have to go to the next turn. So how many turns do we need? 32 turns, yes. So we need 32 turns. Okay, so 32 turns to ensure the accuracy. So you add up the 32 turns, then the error will be less than this. Okay. You think you can do this kind of problem on the homework? Okay. How do you get 1000? Okay, good question. So let's go back here. So from this, we can actually take the reciprocal, right? If we take the reciprocal, then you can get 2n squared. When you take reciprocal, it's going to reverse the equality. So it's greater than 1 over 0.0005, right? Okay. And then divide both sides by, and then what is this? Then this one here is going to be just 2. So it's 2, and how many 0? 1, 2, 3, 4. 1, 2, 3. So it's going to be 2000. Okay, that's 2000. And then divide both sides by 2, then n squared is greater than 1000. Okay, so that's one way to solve it. Okay, like that. Okay, so you need 32 turns. Okay, the good news here, okay, it's the last part here. The good news here, you can have an improved method. It's just like computer sorting, right? You can have bubble sort, you can ask sort, and then you want to optimize which one is a better method, right? So that's the improved method here. So this one say you need 32 turns in order for the error to be less than 0.0005. Okay, now we're going to have a method that you don't need so many turns, and you still have the error less than this. So how does it work? So we could use this n-partial sum and the midpoint method to estimate the sum, and you don't need so many turns. You don't need 32 turns. Okay, how does it work? First, let's know that Rn is less than equal to what integral greater than what integral? What's the integral above here and the integral below here? Okay, okay. Okay, this integral and this integral, okay, of this function, right? So, huh? Oh, just in general, the function. And what's the lower limit for this one? N, yeah, you got it. So this one here will be n, and this one will be n plus 1, right? And then to infinity. Okay, you got this part here, good. Now, if you add Sn, okay, do you guys remember how Sn and Rn relate? Okay, let me go back. So remember Sn, okay, so Sn and Rn add up to the sum, and Rn, so what happens if you use Rn plus Sn? What's Rn plus Sn? That's equal to what? Is it the exact sum? Right? So you sum the first n turn, and here's the remainder. But if you add the remainder with the sum of the first and two, and what do you get? You get the whole thing, right? Okay. So over here, Sn plus Rn is equal to the exact sum. And let's call the exact sum here S. Okay, S is the exact sum. Okay, so let's call that S. So let's call this S over here. Okay, so the exact sum is equal to Sn plus Rn. Okay, so this should add up to this. And then what do we have on here? Over here, we'll just have Sn plus the integral. Here's Sn plus the other integral here, right? Okay, Sn plus that, Sn plus this. Okay. So this is the sum estimate for integral test. Okay, so if you want to estimate the sum, you can use this. Okay. Now from part A, we already got this result, right? We know that R10 is going to, if you use the first tangent, I know that the remainder is no more than this and no less than this. Now after that, you don't need to get more 10. We're going to use the middle point of these two numbers. How do you find the middle point of the two numbers? What's the midpoint? Yes, add them up and then divide by 2, right? So we're going to add them up and divide by 2. Okay, then to estimate. So when you add them up and divide by 2, what's the length for this interval? The length of this interval here is going to be, well, from here to here, the middle. How do you find the length of this interval? Can we find this from here to here, right? How do you find from here to here? Right? Subtract, yeah, using this, subtracting this, you get this, right? And then after that, you're going to use the middle, so we divide it by 2, and this part here is going to be less than 0.0005. Okay, try it on a calculator. Using this, subtract this, and then divide by 2. And you see that number is less than 0.005. Okay, so if we use a middle point to estimate, so I take the middle of these two to estimate the sum, then I know that the error is no more than 0.005. Why? Because the sum is between what and what? Sum is between this and this, right? And then if you take the middle, then it's not going to go, so this is going to be within here to here, so it's no more than 0.005. So by doing this, we don't need to have 3210 to ensure the error. We can just take 1010, and then we see the middle of the two lines, and then the error will be less than 0.005. Okay. All right. So that is the input method. All right. So thank you for coming.